to solve the given system. So let's go over to MATLAB and let's see how we can do this. So we'll say that this is it's problem 3. And we'll split it in parts. So, well, we'll just say part A here. And what's gonna be, first thing, we're gonna clear all previous variables. So that's gonna be clear all command. I'm also gonna clear the outputs there. Good. And now what? Now we're going to define the coefficient matrix. So let's say we have the matrix A, and that is 3, -1, -1 for the first row, 1, 1, -1 for the second row, and 1, -1, and 1 for the third row. We put a semicolon at the end because we don't want to output it. I'll define the forcing function. So that'll be f of t, and that's going to be vector 0, 0, t, and 2 times e to the t. Now that reminds me that I have to declare my variables. So that's going to be the sims command, and I'll declare t for now. Okay, so now that I have defined this, the first thing they asked me to find is finding the fundamental matrix by solving the corresponding homogeneous, and then looking at the vectors, and the vectors are going to be the columns of my fundamental matrix. The vectors and the e to the lambda t. So the first thing I want to check is whether we will have repeated eigenroots or complex eigenroots. We have 3 distinct eigenroots. That's good. I can use the Jordan. Using the Jordan to find eigenvectors and values. So that's going to be vector. It's going to output 2 things, vectors and values. And I can just say Jordan of A, and it'll do that. Then I'm going to define my complementary solution. Actually, not even that. I'm going to define my solutions individually. So one way I can do it is I can say my solution x1, and it's x1 of t, that's going to be equal to the vectors, the first vector that I output. So the colon gives me tells me I'm going to pull the column, the first column, and then it's going to be multiplied by the exponent of the eigenvalue corresponding to that, which is 1, 1, by the way Jordan works, and then times t, and that's going to be my first solution. My second solution is going to be similar to this, but I'm going to put the subscript 2. Here I'm going to put 2, and this is going to be 2 and 2. And this is going to be my second solution. Well, I said I had distinct roots. I actually don't have distinct roots. So this is my second solution. And now I need to find a third solution. So how am I going to find that third solution? Well, once I have this vector right here, I basically need to find the vector p. So how do I find the vector p? Well, I'm going to have my matrix right here. I'm going to copy that matrix, and I'll put it over here. I'll augment it with the value of this vector over here. So let's just see what that vector is first. So we'll output this. Control Enter. Here we get, this is my one of the eigenvectors, and this is the other eigenvector. Now I need to find a third one. Well, if I have 1, 1, 0, I can find the third eigenvector. And Jordan gives it to you, but let's just check, right? Find the third eigenvector. So to find that, I'm going to have this matrix over here. Copy that, paste. I'm going to augment it, and it's going to be equal to this. So it's going to be 1, 1, and 0. And then I'm going to put this eigenvalue in, which is the eigenvalue of 2, in the diagonal. So 3 minus 2, that's 1. Then 1 minus 2, that's -2, -1. And then 1 minus 2, that's -1. And then I'm going to put this in reduced row echelon form. If I do this, I should get a way to find the third vector. It actually tells me that I could have found it regardless, because in this case, having done RREF, I see that, so really, let's pretend I didn't write this, and I do RREF because I notice that these are repeated values, and I do it with the 0. So what do I get? Control Enter, I get the following. So I get that I can decide 2 variables, call it y and z. So I can say that k, this is one vector. I can say that k2 is going to be the vector, see, I can decide both y and z. So let's say y is 1 and z is 1. And so I'm going to say that x is going to be the sum of 1 and 1. So that's going to be 2. And I didn't have to choose that, but this works. And now we're going to do k3. As long as we put a 0 somewhere, we know that that's going to be linearly independent. So let's say we have 1 and 0, then that's going to be 1, 1, and 0. So these are going to be my vectors. So I can defining the other two solutions. And so now I'm going to write that x2 is equal to k2 multiplied by, no, it's not going to be multiplied by a vector. It's going to be multiplied by e to the t, because we're going to have, well, to the 2t, because we're going to have the coefficient of that same vector. And x3 is going to be equal to this same thing, but it's going to be k3. And so these are my 3 solutions. They're all functions of t. And now, why is this useful? Well, because now I can define my fundamental matrix, which is going to be a matrix phi, which is a function of time, with these 3, x1, x2, x3. Notice how I put a comma, I don't put a semicolon in this case, because these are vectors, and this is the way to write them in columns. So that's my fundamental matrix, and that will answer part A. Then in part B, they want me to find the inverse. So finding the inverse of phi, I'll call it pho. That's going to be inverse of phi of t. Oh, we don't even have to write the t. And then, once we have that, they want us to find f of t. F of t, we've already defined it over here, so we already know what that is. And now they want us to find u. So finding u of u of t, if you remember, u of t is equal to the integral of pho, the inverse of the fundamental matrix, times f of t. And then once we have that, I'm going to find the particular solution, which is going to be just phi of t times u of t. And then I can check it, checking the particular solution. So to check it, I want to take the derivative of xp, and I want to see if that is equal to a times xp plus f. I'm going to press Control Enter and see what this code outputs. So here we see that we may have made a mistake because we don't see that the left is equal to the right, although we might try expand and simplify right here and see where that leads. And I forgot a parenthesis here. And actually we are correct. It was hard to see. So this is the variation of parameters. First you want to check. You want to define your matrix, coefficient matrix. You want to define your forcing function. You want to check if you have a multiplicity case, distinct eigenvalues, complex eigenvalues, then go from there. So if you have distinct eigenvalues, I thought I had them, use the Jordan. Otherwise, don't use the Jordan, but I did. And I used the Jordan to define the first eigenvector. Then the other two I had repeated roots, so I had to do the augmented matrix, and then I realized that it was one of those cases where I could actually find the two independent eigenvectors without resorting to the other guessing method. So I did define them here, and then I defined my three solutions, one here and the other two here. And then I found my fundamental matrix by putting each solution in a column with the comma, and then I found the inverse with the inverse command. Then I found the u of t by taking the integral of the inverse times the forcing function, and then I multiplied u of t times the fundamental matrix to get the particular solution. So now if you want to find the overall solution of the system, but that wasn't required, then we could add the particular solutions in linear combinations and the general solution, the complementary solution, and the particular solution. I hope this was helpful. I know this might have been a little bit difficult to visualize doing it on the computer. I still don't have a good way to write and do the computer videos at the same time, so I apologize if this was a little bit unclear. But I hope that if you did all the other videos, this wasn't too hard to follow. And I'll see you next time.